In this video, we're going to see a randomized version of Quicksort, which will have a better average case runtime than the deterministic Quicksort. But before we get into that, I want to give you a little bit of a background on randomized algorithms. You're only going to see a couple of them in this class, but these are interesting from the standpoint of usually we imagine algorithms as being deterministic, something which has given some input, has some series of consecutive deterministic steps, so that if you were to run this again with the exact same input, you would have the same series of steps which is executed. And with a randomized algorithm, we don't have that. We introduce some element of randomization into our algorithm. And there's two types of randomized algorithms that you'll see. One is called Las Vegas, and the other one is called Monte Carlo. And the Las Vegas one, this was originally introduced by a Hungarian professor at the University of Chicago named Laszlo Babai. And the reason why these both have kind of names which you may associate with gambling is because we're gambling with something, either that the output is correct or that the runtime is some fixed function. So with the Las Vegas style randomized algorithm, we guarantee that we will get the correct output no matter what, but we're gambling a little with the runtime. You may say that it has an average runtime of some function, average runtime of n log n, but it's not guaranteed. It's a gamble. With the Monte Carlo style randomized algorithm, we can guarantee that the runtime will be some function, that it will always be linear or n log n, but we gamble a little with the output. It might not be correct. Maybe we can show that 99% of the time you get the right output, but there's a small sliver of a chance that you would get the wrong output. And sometimes this is good enough. Now what we're going to see today is a Las Vegas style randomized algorithm where our randomized quicksort will guarantee at the end of this we will definitely have a sorted list. There is no question about that. But we gamble a little bit with the running time. And how this is the case is our randomization, what we're going to use is we're going to pick, rather than deterministically we pick some pivot, we're going to randomly select some pivot. So our randomized quicksort will randomly choose some element as our pivot, at least pseudo-randomly. It still has a worst case running time of big O n squared, still quadratic worst case running time, but we'll see that the probability of this happening is pretty low. So it's not likely that we would happen to choose the worst case randomly every single time. So we'll be able to show that the expected running time is n log n. So with randomized quicksort, this is the same quicksort that you've seen before. The only difference is that we randomly pick our partition. So given some input sequence, we use a random number generator in order to choose what index between 0 and the size of our list, what index will be our pivot element. And then we use that item to break up our list into everything less than that pivot, everything equal to our pivot, which isn't shown here, and everything greater than our pivot. And then after our recursive calls, we have sorted lists L and G. We put them together as everything less than our list, equal to, and greater than our list now that they're already sorted. So it should be clear why this still has a worst case running time of big O of n squared. This is the same reason as our deterministic quicksort. If we're unfortunate that we pick a bad pivot each time, maybe we pick the unique minimum or the unique maximum, even just that partitioning step, if we have maybe n minus 1 n elements the first time, n minus 1 elements the next time, n minus 2 elements the next time, and etc. Every time we pick a pivot, we only remove kind of one element from our sequence that we're working with. And we do this every single time. Our total running time would be the sum of these elements, the sum of these numbers, which is quadratic. But it might not be clear why this has an expected running time of n log n, whereas our deterministic quicksort doesn't. And the main reason for this is because when we randomly choose a pivot, without knowing anything about the distribution of our input data, if it's randomly, if it has a random distribution or not, without knowing anything about our input, when we randomly select a pivot, we can show that we pick a good pivot half of the time. And what do I mean by a good pivot? So we can classify a pivot or a call as being good or bad based on whether it kind of evenly distributes elements into those lists L and G less than and greater than our pivot. And rather than being very strict in saying that it has to evenly divide our input into half and half like we did with merge sort, we're going to be a little bit less restrictive and say that we just want to break it up so that each list is no more than 3/4 the size of our original input. So a good pivot is one which guarantees that the lists L and G, neither one of them is too large. Each of them is no more than 3/4 the size. So let's say less than or equal to 3/4 the size of our original input. So if we had S elements, this would be 3/4 the size of S. Right? Whereas a bad pivot would be one which unevenly distributes these lists so that one of them, maybe the list L or the list G, but one of them has a size greater than 3/4 of our original input. So we want to count up how many pivots would be good and how many of them would be bad, so that we can say something about what are the odds that we would pick a good pivot out of all of the numbers that all of the elements that we have, how many of them are good and how many of them are bad. Now, in order to count up how many are good, we're going to imagine that our list is already sorted. So we know it's not sorted initially. This is our job of what Quicksort wants to perform. But just to count up how many pivots are good, this will be easier for us to count if we visualize them as being already sorted. Because in this case, we can break up our list into 4 quadrants. We have kind of the first n over 4 items, the second n over 4 items, third, and the fourth n over 4 items. So 4 quadrants here. Now, if we were to pick anything in the first quadrant, this would be a bad pivot because we can see, since these are already sorted, if we were to pick any one of these items here, for example, that all of the items to the right of it would be greater than it, which means we would have our list G, everything greater than this pivot, would be more than 3/4 the size of our input. So these would all be bad pivots. And for the same reason, we can say if we chose anything in the last quadrant, since we have 3/4 of our sequence are less than every item over here, if we were to choose any one of these last quarter of items from our sequence, if the sequence is already sorted, as a pivot, then we would have more than 3/4 of items which are less than it. So this would also be a bad pivot. So in this already sorted sequence, we have that the first quarter are bad pivots, the last quarter are bad pivots, but anything in the middle here would be good because this would kind of evenly distribute these lists in the way that we want. So where we have no more than 3/4 less than this item or no more than 3/4 greater than this item. So anything in the second or third quadrant would be okay from the standpoint of what we define a good call as being. So again, our sequence, what we're given, isn't sorted. At least we don't know if it's sorted already, but we're just using this in order to count how many pivots, we don't know where they're at, but how many of them are good. And from this standpoint, we see that half of them are bad, but half of them are good. So they might be anywhere, those good ones, the beginning or the end, since our sequence isn't sorted, but we know that half of them will be good, which means that the probability that we would pick a good call is half. So there's a 50% chance we have of picking a good call when we define a good call in this way. Okay, so this will be important in showing that the expected runtime, our average case runtime, is good. Half the time we can expect to make a good call. A good call meaning that, not that we evenly divide our list by half, but that we divide our list so that at least no side L or G is more than 3/4 the size of our original input. Right? So half the time we can guarantee this. Now, we're going to use the probabilistic fact that if we flip a fair coin, the expected number of times we'd have to toss that coin in order to get K heads, if there's a 50% chance of getting heads, is 2 times K. And we can apply this for the expected number of times that we would have to make a call to quicksort until we get a good call. So if we want to get a good call k times, we would have to, the expected number of times we would have to call this is 2k. So we've got here, we're going to use the same kind of visualization that we did for merge sort, except here we're looking at the execution of quicksort. So this is one recursive call to quicksort, and we've got the lists L and the list G. Note that they might be different sizes now. And we're going to count up how long it takes for quicksort to execute by considering how much time we spend at each level of these recursive calls, and then how many levels of recursive calls we have. So we know that the amount of time that we spend per level, with merge sort, the amount of time we spent, the non-recursive calls, the non-recursive overhead that we took was spent on merging elements. With quicksort, the non-recursive overhead that we get comes from our pre-processing step of partitioning elements. But we have a linear amount of time that we spend at each level just partitioning elements with quicksort. So this is picking some pivot and then saying, here's everything less than that pivot, here's everything greater than that pivot. For this list, here's everything less than our pivot and greater than our pivot. But at each level, if we count up how many elements that we have left, the amount of time we have is linear. So the only question remains, how many levels do we have? So how many recursive calls to quicksort would we have to make? And what we can show is that similarly to merge sort, with merge sort we were dividing our list in half each time, and so we could show that the height of this tree was log base 2 of n, because we could guarantee we were always dividing our list by half each time. And log n was the number of times we had to repeatedly divide our list by 2 until we were left with 1, and that was our base case here. But with randomized quicksort, this is a little bit different because we're not dividing our list by half, but we can show when we have a good call that we divide our list by, we're left with 3/4, no more than 3/4 of our original input. But we also don't have that this happens every time. Maybe we have a bad call sometimes, we're picking our pivot randomly, but we can expect that this happens half the time. So if we made I calls so far, we can expect that half of the time, I over 2 of the time, they're good calls from the standpoint that the size of our list which remains is 3/4 the size of our original input. So the question becomes, how many times do we have to do this until we're left with 1? Meaning we finished. We're at a leaf in our recursion tree here, just one element left. We have nothing left to sort, so we're done. And we can solve for this just like we did with merge sort. So we're going to multiply by 4 over 3 to the power of I over 2 in order to make this left side equal 1, and we're going to be left with, let me write it up here, we'll have n is equal to 4 over 3 to the power of I over 2. So I'm just multiplying 4 over 3 to the power of I over 2 on either side, not changing our equality, and we're left with n is equal to 1 times that value. And now we want to solve for I, because I is telling us how many times we have to make a recursive call to quicksort until we're left with 1. So in order to solve for I and get rid of this base, since I is in our exponent, we're going to take log base 4/3. So I'll have of both sides. So I have here log base 4/3 of n is equal to log base 4/3 of 4/3 to the power of I over 2. And this will cancel our base out, so we're left here with just I over 2. And when we want to solve for I, we'll multiply by 2 on either side, and we're left with I is equal to 2 times log base 4 over 3 of n. This is what we've got here. If we have, if we're at this depth, then we can expect that the size of nodes at that depth, the size of our input sequence, would be 1, which would be the end of our recursive call. Now it doesn't matter what base of n, what base of logarithm we're using here, because we can go in between different bases, changing only by a constant amount. So this is kind of already omitted here. But because of this, we can show that the expected height of our recursion tree is logarithmic. So getting rid of our constant coefficient, doesn't matter which base we're using either, the expected height of our tree is log n. This is because half of the time that we make a call, we expect it to be good in the sense that we're left with 3/4 the size of our input. So that means that the total expected time that our randomized quicksort takes is the expected height of our tree, how many levels we have, which is log n, times how much time we spend at each level, which is n. So our total expected time is n times log n, which means the expected runtime of quicksort is big O of n log n. So this is our average case. Still, our worst case is big O of n squared. This is if we're very unfortunate that we pick a bad pivot each time, but we don't expect for that to happen. The average case is big O n log n. Okay, now we can also implement this in place, but we're going to see that in the next video. If you have any questions, please post on Piazza.